some there. All right. Make sure that the, oh, I hear audio. Oh. Everybody's getting a ding. Give it a second because this silly thing is. Okay, wait a minute. Oh, that's where the. Okay. Next, let's see. I think this. Let's see if this will load. Oh, there you go. Well, I'm going to do one problem and then move on to the second problem. And let's see. So if I put up an X and a Y and consider this a distance B and this a distance H. Oh, wait a minute. Sorry about that. Hang on. Okay, I think it's coming on. Okay. So in the book, which I believe, which one of these was it? There it is. So in the book, he defines these two terms, which are important for mechanics of materials a lot later, like very important. But we'll just do one of them. I don't know. Let's see. X squared. And there are two ways to think about it, the way the guy does in the book and another way. And what we'll do first is we'll kind of mimic or take a look at what he does. First of all, that's kind of standard. But we're going to try to get the same answers and possibly look at it a little bit differently going forward. Since I have X in there, it's best to break this into somehow that has a dx, which means that. Now I'm going to mimic what he does in the book first, and then I'm going to show a different way of doing it. his particular case, dx is equal to that. And he might do that, I don't know. And we go from 0 to b. Let's make sure that, wait a minute, which one was it? That one. Oh, he did the y first. Well, it really doesn't matter. Oh, that's the wrong thing. Go to there, to there. So, here. Oops. Sorry about that. You got h in the denominator that wasn't supposed to be there. That's a b. So, you end up with h b to the third over 3. That's a fairly easy integral. What we're going to do is do the problem again, recognizing that the centroid sits right in the middle, and we're going to put a coordinate system here. This time, this will be minus b over 2, and then b over 2 minus h over 2, and then to h over 2. You set up your integral as well. And you have the same thing, dA is equal to, still the distance between here and here is h. So you have x squared h dx, but this time you go from minus h, I'm sorry, b over 2. So you're starting here, you're going across to here, b over 2 ends up being got that right, minus b over 2 and b over 2 ends up being h, and I'll just put the 3 there, 2 to the third, and then minus to the third. Okay, so since that's cubic and that comes out as a plus, I'll get 2, because there's 2 of them, I move that 2 up too high. Okay, put the 2 down here, and then b to the third over 2 to 2 to 2 is equal to 8, but I could say it's 4 times 8 over 3. Okay, wait a minute, what did I do wrong? Let me complete it out. Okay, so 2, why do I have that down there? Let me get rid of this. Do it like that. Get that canceling. Then I get height, base to the third, and these go together to give you 12. So the first thing you find out wrong thing. Let's go back. To here. So what I was actually solving technically was this. I know there's one subscript, there should be two because it's a tensor. But what that comes down to is I get two different answers based upon where I put my coordinate systems. So it turns out, and without too much discussion, and this one is a special version of one because this is where the coordinate system is centered and on or at the centroid. Now, if you wanted to go in here and take the centroid location and say, this one's a special one. Now, let's say I did this. Okay, Alt, I'll go into blue. I will shift it out here in a new coordinate system. So we've already seen that they change based on the coordinate system. And what I'll do, let's see, what do I want to call that? I'll call it delta. Not delta x and delta y. So there's a unique thing here in that if I were to integrate the area and I were to do it with this particular one, then you might ask the question, which coordinate do I use? And for the sake of argument, I'm going to use this one and relate it back to the original. So if I were to do that, I'll start with this concept. That is, if I were to start and put a bar out here, that were to sit right here, had a dx, I would be integrating. I'll have to slide down, or maybe not. I would be changing the coordinate system such that, let's put it like this, x from this original one plus delta x is equal to x bar. In other words, if I'm looking at any particular location, case in point, let's say I'm looking at a stripe right here, or anywhere, a line that's vertical right here, and I have a coordinate system sitting here like this, and let's just say a case in point, if I were to look at, here, let me move it the other direction, here. Okay, I have my point here, and I have my centroid point, and I'm looking right here. This distance would be x, this distance would be x bar, meaning I've got what I've written here actually backwards. So if I added this component to that component, it would be the same distance as this one. So therefore I can take this and put in here, and I'll have this d area, which actually becomes squared, which if you do the math, you get this squared plus 2 plus, so the first time you see something interesting, and that is that we saw before that we had one answer here, and we had the second answer here for the same question, but had different coordinate systems. So now I'm going to use this to relate these two, and the reason this is special will become apparent in a second, because actually I did this in a reverse way. I wanted, let's say we want to do this. I don't want to find it, so right now I'm finding it about the centroid. What I want to do is find it right here. And actually he may come up with this. Let's see if he does. He just writes down a Parallexis theorem. Actually, I guess we could go with it from what he's got. That would save me a little time. And that is, he's picked himself a location. Let's see if this works. Doesn't work on this, but it does work if you launch this in, okay, open with, let's see if it works here. Oh, it does work. Oh, I lost my, okay, hang on That's not what I wanted. I feel like I'm wasting too much time. What I was trying to get at was this, and I'll just use his. So he has a new, so he has an old axis. He has a new axis. And he's put the primed new axis on the centroid. Now what he's wanting to do is he's wanting to find the moment, and he's doing, instead of doing the XDA, which it doesn't really matter which one you do, the Parallexis Theorem works fine for both. So what he's done is he's recognized that to get yourself to this particular area, and using it as a y, you can either start from here or you can start from here. But if you add this to that, you get the same as if you just measured from the original. So what he's doing is taking this and using a constant shift and this is important that you realize it's constant. Then he just carries this out. What he does next is he does the one step I did, which is y prime squared plus 2 y prime dy, which he uses dy instead of my delta, plus dy squared. So he takes the dy squared, puts it right here, the 2 and the y right here, and then this. Now, let's see. Oh, okay. If I'm doing an eraser, okay, I'm wasting time here too. That's a marker where I don't know what that is. I don't know what that is. I'm looking for an eraser. And, oh. Geez. I don't know that it's going to disappear. Oh. So one of the things that's interesting here is this term. Since the y prime and the x prime was placed on the centroid, then if you look for the centroid of an object in which you place the origin on the centroid, you find out this. So the centroid related to that origin is this. Related to this origin, the centroid is, for x, would be dx. For y, it would be dy. That's not derivative, that's just a distance. So you end up with something that's called the Parallexis Theorem, which is essentially this, which is at the centroid plus this distance, which is this term, this one becomes 0. Why? Because it is by definition the location of the centroid. So you look at this term, and that's just the area right here. So you end up, and I think oh, it did disappear. Okay, so on the next page, you see this. This is related to the centroid location. This is the distance away from the centroid. That's, of course, the area. That's the x distance. I should have mentioned that's the y distance. This is the x distance. So let's test it out on what we've done. So since his derivation was fine, I'm just going to stop what I was doing and go on from here and then use the Parallexis theorem for this simple case. And say, we had our centroid right here, it became is equal to h. If you scroll up a second, you'll see h base to the third over 12. Now, if I move this location down to here and then back to here, I get a new coordinate. This distance, I have to remember, this is b over 2 minus b over 2, h over 2, h over 2 here, positive on top, negative on the bottom. So what you end up with is, if you're wanting to know I, y, y about this location, it's equal to the centroid, y, y, which he has 1 y, but I keep writing 2, plus the distance, okay, if you look back, the distance, and I should have put the area, but here, I'll put the area here. Remember, looking back at here, here's the location here. So we are working in the confines of this one. Now I can't get that to come back up. Anyway, oh no, it was over here. We're working in the let me get rid of this one then. We're working inside of this one. So the area is base times height. The dx, the distance from here to here, base over 2, and I forgot one term there, the squared term, plus where this is at the centroid, so it's 1/12, or let me just look up here. Now, does this one equal the one that's way up at the top? Now, let's see, if I square this, and I get height on this term just here, height times base to the third. I'm squaring that, so I get a 4. Or I get a 3. 3 times top and bottom. And then I add this 3 to this 1 to give me 4/12 of h biased to the 3. And then I can break that back down to 3 times 4, knock that out, and get h base to the third over 3. The question is that the same thing that occurred up here? And in fact, if you look at it, that is. You look at it up here, h base to the third over 3, and h base to the third over 3. Now, okay, so that's an introduction kind of to the Parallexis Theorem, but let's move to the next part, which is the part that let's look at the way he solves it, and let's compare that. And this will take some time to compare that to what you were taught in Cal 2, because I think they're quite a bit different. That looks like a good enough problem right there. So, and he has decided to solve that. Does he solve the other one? Wait a minute. IX. He doesn't solve. He only solves IX here. Okay, so let's stare at what he does. And then what we're going to do is approach this differently. What he does is he goes in and does this. And what I'm going to do is I'm going to show you a different way that's more related to what you've seen before. After get all this stuff off of here. Okay, here's the way I'm going to do it. Okay, wait a minute. Go ahead and take this. And then I'm going to look at what he does, and I'm going to approach it completely different, but I'm going to basically copy over. Now I'll copy all that. And drop it right there. Okay. Alright. So he starts it this way. But the way you were taught, kind of in, I mean, I'm assuming the way I was taught is take a little D area here, and then you have to decide whether you're running it up and down first or left and right first. The key here in the decision is this. So your D area can translate into something like that. Now the question is, which one do you do first? And that, okay. Depends on how your limits are going. In general, it may be better to do it this way. Oh, okay, here. Now, if you look at dx, okay, your x limit, let me scoot these apart. Okay, first thing you usually saw is the y, and then you saw the x. So in actuality, you may see something like that. So before we decide which one we're going to do, let's take a look at something. What you find out, let's see. He has this. So it's okay. Let's take a look at this. $100 minus x. So what he has done, that's because this is 100. So your limit, if you look at this distance, this is x. So this is what we're looking at for the most part. And x is that, according to this line. I'm sorry, this curve. So there's your first limit. And your second limit is to here. So wherever you are in y, you're going to go from here to here. So you might want to call this lower limit, x upper limit, to be just 100. So if I went out here and put an integral of 100 and y squared over 400, and then I recognize something interesting. This is my dx. So in effect, since this is a function of y, I have to exchange these. In other words, I have to rewrite it I'll put a block here. So in fact, you look at this, there's nothing more that comes out of here except the integral from 1 to y squared over 400. Actually, the upper limit, I've got those backwards. This is the lower limit. So let me see if I can use a combination of it goes from and it goes to 100. Upper limit, lower limit. Fix that. All it does is swap the sign. So you get 100 minus this. Now, the reason I go this direction is that although he has it listed this way, by looking at this part right here, in fact, it's the same thing that you would have done in Cal whatever, where now you have this, and the y goes from pretty simply from here to the top, which is 0 to 200. Now, if you look at what you did in whatever the calculus course that had these double integrals in them, and what he has, it's the same thing. Oh, I forgot the squared. Except that what he did in this book is he drew it differently. And this will work all the time. The old way you learned works all the time. The reason I try to avoid it, his method doesn't have anything to do with this one. It has to do with this one. If you look at what he does here in case 2, this can be a point of confusion, but what you find out is he goes in and does this integral here, and notice what he's doing here. He's doing the Ix with the differential here. He's doing the Ix with the, oh, I should have done it right here, with the differential dx. How does he get around doing that? What he does is he says there's an element that's like a tower here. And what it has a centroid halfway up. This is the top. And then what he finds out is, what is the I about the centroid? He uses the formula that was derived a page before. 1/12 base times height to the third. And then he uses the Parallexis Theorem to draw it back down to right here, to this origin right here. And he ends up with an equation right here. And that is basically the di of the strip. And then he comes in and does it this way. He integrates that, goes through the process, finds the same answer. This method can be confusing, to say the least, because you're always having to take a little di. In other words, if the bar is going in this direction, and I'm doing the di and have the bar going vertical, I always have to do it this way. But it's your choice. You can choose the method, which this actually is the method of Calc 2 maybe. And this is a new method which depends on the Parallexis Theorem and a di. So some people find this problematic and have problems with that, but it works well. It works the same with both. And you can look at it again here. So if you look at this, you see a dy. What he's done here is he's decided to have a dx. And again, what you have to do is you have to find this is a long slender piece, and the base is dx, height turns out to be this, or 2y, because there's one y below, one y above, and you end up with this being the dix, and then you have to integrate it, end up with the same answer on both. So Oh, it looks like it's done.